Swayam Prabha. Digital India. Educated India.
Some people have found the answer to this little question we had of the probability that there are exactly little n molecules inside a sub-volume V in this situation. And the way you go about it is as follows. You start by saying that if a particle is inside this little volume V, what's the probability that it's actually a priori inside? Since it is uniformly distributed, it could be anywhere with equal probability, there's no bias anywhere at all. The probability that it's inside this little little cell is V divided by capital V. If little v becomes capital V, the probability is 1 that it's inside the big box. That's obvious. And if little v is 0, the probability is 0. So the limits are all right. Okay. The physical assumption is that these particles, the molecules are spread out everywhere uniformly and that they don't talk to each other. They collide with each other, elastic collisions and so on, but otherwise there's no interaction at all. Otherwise, if there's an interaction, this is not true because they tend to clump together or repel each other or something. And you want exactly n of these particles to be inside, the probability for that is n. So if you regard success as the probability that it's inside the sub-volume V, then we have P is equal to little v over capital V. This is the translation from the binomial distribution to this particular problem. It's not enough that little n of the particles are inside, just as it's not enough that capital H of them are heads. You also have to ask what happens to the remaining particles. They must be outside. The probability of being outside is 1 minus v over for any given particle, and you must have exactly n minus n of these outside. So this is like p to the power h, q to the power n minus h. It's exactly like that. And you don't care which particles are inside out of the full number. Some little n of the capital N particles have to be in. So the answer is NC. Because you can choose the little n particles in any number of NCN ways out of a capital N total number of ways. You don't care which particles are inside. If you put labels on the particles and say I want only these particles inside, then it's a different answer altogether. Okay. So it's a binomial distribution. Let's put in some numbers and see how small this is. Let's take this room. Assume that the volume is 10 meter cubed or something like that. So 10 cubes on each side. So capital V is 10 meters on each side. So it's 10 to the 3 meter cubed. Little v is 1 meter cubed. So P is equal to 10 to the minus 3. The ratio of the two is 10 to the minus 3. And you have to put that in and put what capital N is. How many molecules do you think there are in this room? Assume that it's an ideal gas, and how many do you think are inside this room? Well, the ideal gas equation, yeah. So it depends on the number of moles, but approximately how many particles do you think there are in this room? Just give or take an order of magnitude. Certainly more than Avogadro's number, there's more than one. About 10 to the 24, maybe even 25, etc. So it's a huge number, and you can estimate what this probability is. So put in those numbers and see what happens here. Okay. How many particles are there inside this sub-volume on the average? You can ask what's the average value of little n.
How large are we considering small v?
Pardon me?
How large are we considering small v to be?
1 meter cubed. It doesn't matter. Could be anywhere from capital V to 0. Doesn't matter. Just for argument's sake, I'm saying 1 meter cubed at the corner. Okay. What is the average value? So we are asking what's the average value in a binomial distribution. This is a binomial distribution. The language, the translation between the two languages is given by this here. What do you think is the average number? You can work this out from the binomial distribution, but let's give a physical argument as to how much it should be. What do you think it should be on the average? It's fluctuating all the time about some average value, but what do you think is a steady average? He's guessed it, but let's see whether he is right or wrong. N into divided by capital B. How do you interpret this? The answer is right, but how do you interpret it? Yeah, so if you have, quite right, if you have capital N particles inside a volume V, the average number density rho is N divided by V. This is the net number density, number of particles per unit volume is the total number of particles divided by the total volume. Okay. And the number inside any sub-volume is the average density multiplied by the volume concerned, which is little v. We can now ask for the fluctuations, what the second mean is, the moment is, what the variance is, etc. I am going to introduce the idea of variance very shortly. Okay. But let's go back and ask, is there a simple way of finding out all these averages? And let's see in the binomial distribution itself whether there is a simple way of finding the average values. And let's do it this way. It's a very powerful method of doing so. It's just a piece of algebra, but it helps. We go back to our coin tossing experiment in which we found that P n of h was equal to NC h times P to the power h Q to the power n minus h. And h took values in the set 0, 1, 2 up to capital N. We also know by normalization of this probability that h running from 0 up to capital N, P n of h is equal to 1. This is called normalization. The total probability is 1 for any random variable. It's a proper random variable. Okay. Probabilities cannot be negative. They can be 0. Some event may have 0 probability, but they cannot be 0. And the total probability must be 1. So it's clear that each individual probability must be some number between 0 and 1. Okay. So those are the criteria that you have to use always. And we'd like to know what's the average number. The average, also called the mean, is denoted by this h, and it's the weighted sum of h times P n of h, summation over all possible values of h divided by the total probability So you weight each value of h by its corresponding probability and you normalize the probability. Sometimes this quantity is called the frequency of appearance. So in statistics books you will see frequency of appearance of h, any given h, it's given by that. But in our problem we have normalized this probability, so the denominator is equal to 1 because of this condition. So when you use probabilities, make sure it's normalized, otherwise you have to divide by this normalization factor. And we need this quantity, where h, Pn of h is given by this. So you have a binomial coefficient and you're going to multiply it by this h and then have sum over h. Looks like a tough task because we know the answer for the sum of binomial coefficients. This is just p plus q to the power n. But what happens if you multiply by h? Then you get a series which is not so trivial. We need a little trick here to do this. What should we do? What should we do? We use a trick. The most convenient trick is called the generating function method, and let me say what it is. Instead of considering Pn of h, you consider a slightly different quantity. You consider a function of a variable x which I introduce from outside. X is a variable, it takes on real values. Okay. Later we'll generalize even that, it could take on complex values, but we don't need that here. It takes on real values. To remind myself that I'm talking about a problem of n coins being tossed, where n is given to me, some fixed number, I'm going to put a little subscript here. If n changes, that function also changes. And it's defined as summation h is equal to 0 to n x to the power Pn of h x to the power h. That's my definition. What sort of function of x is this fn of x? Is it an exponential function? Is it a trigonometric function? Is it an algebraic function? It's a polynomial function. Why do you say polynomial? We are adding different powers of x, yes, but up to a finite value, only up to n. Therefore, it's an nth order polynomial. If your distribution went all the way to infinity, the sample space, this would also go to infinity, then it's not a polynomial at all. It's a power series. Okay. So, is this clear? It's a trivial matter, but is it clear that it's a polynomial in x? What's the order of the polynomial? N. And what's the coefficient of any power of x in this polynomial? The corresponding probability, Pn of h, right? So, I'm going to consider this function. Does anyone have any objections to my considering this function? There's no law against it, yeah?
So here x is it's just some other variable. It's
It's not
not related to any.
related to any of this. I just introduce it from outside. Continuous variable.
You're limiting it to n because you need sample space. But the sample
Yeah, no. I'm going to define x is a continuous variable, a real variable, and I'm just multiplying each Pn of h by x to the power h, that h, and summing over h. The answer is clearly a function of n and a function of x. H is summed over. Okay. What's this going to get us? Well, let's simplify it. This is equal to summation h is equal to 0 to n. For Pn of h, I'm going to write nch, p to the power h, q to the power n minus h, times x to the power h. I multiply each Pn of h by x to the power h, where x is a variable I just introduced for fun, apparently, okay, and that's the term. You agree I can combine this ph, p to the power h and x to the power h and write this as px. It's just px to the power h. Can I sum this series? Px plus q to the power n, right? It's just the binomial series. So we find by the binomial theorem. What is f of 1? If I put x equal to 1, what should I get? F of 1 should be equal to 1. It better be, because f of 1, if you put x equal to 1, you get summation Pn of h, which is normalized to unity. So you should get 1. Do you get 1?
Yes.
So Fn that checks. That's a check always on the generating function. You put x equal to 1 in the generating function, you should get 1. It's normalized, right? Have you studied some differential calculus? Do you know how to differentiate x to the power n?
Yes.
Good, that's all we need here. What is df? What is fn prime?
And into dx plus
What's that equal to?
n dx plus dx minus 1 power n minus 1 into p.
I differentiate the power of x, I get nx to the n minus 1, etc. But if I differentiate here, what happens? By the way, I use a prime for derivative. I hope that's standard notation. You approve? Good. What is this equal to? I have to differentiate the x in this formula. Hx to the power. So it's inside, the derivative is inside, so this is equal to h, x to the power h minus 1. On the one hand, the derivative is equal to this. On the other hand, the derivative is also equal to this. These two must be equal. What happens if I put x equal to 1 after I differentiate? No. What is fn prime of 1 equal to dfn by dx at x set at x equal to 1? What's that equal to here? Because this becomes 1. And you have an n here and you have a p there. So this becomes np. But what happens here? So fn prime of 1 is equal to what? This x to the h minus 1 goes away because you put it equal to 1. You put x equal to 1. And what's that equal to? No, what's the definition? It's the weighted sum over h times the probability of h divided by a normalization 1, and that's the average value by definition. So this is equal to h.
So why is that the average?
That's the definition of the average, the weighted sum. The variable multiplied by the probability of that variable having a particular value divided by the normalization factor, which in our case is 1. So did we sum any complicated series or did we just differentiate x to the power n? Yeah, so it's a trivial way of doing it. So you see the power, now you'll see the power of this generating function method. So the average value is np, and let's check quickly whether it agrees with our physical intuition or not. If you toss the coin a large number of times n, what's the average value that you expect if it's a fair coin? That you expect heads. You expect roughly half of it will be heads, and that's indeed true. If the coin is biased such that you practically have no probability of heads but almost always tails, this goes to 0. And if you have a coin where it's almost always heads, almost all coin tosses are going to give you heads, so it's close to n. So it's close to n on both sides and it hits the middle correctly, right? So this is a fundamental result. For all Bernoulli processes for which only 2 outcomes are possible, if there are n trials, the average number of successes is the number of trials multiplied by the probability of success in a given trial, in an individual trial. It's a basic result. Yeah. How I got? My argument is the following. Independent of the method by which we do this, the mean value h is defined. It's defined as each allowed value of h multiplied by the weight factor, which is the probability of getting that value, summed over all possible values. That's the definition of the mean. So by definition, this is equal to the summation over the random variable h's possible values times the probability that you have in particular h multiplied by h. It's a weighted sum. So sum over all values h, but each of them is weighted by the corresponding probability. That's my definition. And what I did was to introduce a variable x to create a generating function for this probability distribution, and then found that when you put x equal to 1, you get normalization correctly. And if you differentiate with respect to x and then put x equal to 1, you get a formula for the mean. What's the mean square value? What's the definition of the mean square? So you square this and then take the mean. What's this equal to? This requires much harder calculation, but the definition of it is this. You take the square of the h and multiply by the corresponding probability and sum. So the question is there a trick using the generating function to find the mean square value? First of all, I hope you appreciate the fact that we've got careful notation here. H squared is not equal to h squared. The square of the mean is not equal to the mean of the square. Certainly not. They are very different quantities altogether. We are going to come back to this and see what the significance is. But which one do you think is bigger? This is bigger or that's bigger? Is this bigger? I mean, just think of a random variable which can take, just for illustration's sake, suppose the variable can take on positive as well as negative values. Which do you think is bigger? If the variable is denoted by some, I'm going to use some symbol for this variable. Let me use a complicated Greek symbol, xi. Greater than or less than question mark, xi squared. Which do you think is bigger? A priori, with no other further knowledge. Given a random variable which takes real values, which do you think is bigger? This mean square is bigger than the square of the mean? Why do you say that? It's true, but why do you say that?
Because when you're taking the mean, the negative values will bring down the...
Yeah, it's possible this mean is 0. It's entirely possible the mean is 0. But the mean square is not 0. What's the average velocity of the molecules in this room? Or given molecule, what's the average velocity? It's undergoing collisions with the walls, with other molecules, etc. What do you think is the average velocity of the particle in this room? Pardon me? Velocity, not speed, average velocity. Average velocity of the molecule in this room? 0. It's not going anywhere. Right? The whole room is not being transported anywhere. It's not going anywhere. The average value is 0. What's the mean square value of the velocity? When you multiply the mean square velocity by the half times the mass of the molecule, you get the mean kinetic energy, the average kinetic energy. Is that 0? What's it equal to? 3 kT, Boltzmann constant times T, 3 over 2 kT. So it's not 0. The word temperature is another word for the mean kinetic energy of molecules. Just another word. It's a historical accident. It should never have been introduced. Just a word for energy. It was introduced at a time when people didn't understand the nature of what heat is. They thought there was some mysterious caloric fluid inside the solid and then inside a heated object which would be transferred when you put it in contact with a colder object and so on. A lot of nonsense, some of which is still in your textbooks. But now we understand the nature of heat. What is heat energy? It's the kinetic energy, mean kinetic energy of random molecular motion. So we should just have used energy as the unit. We shouldn't have used temperature as the unit at all. So we need a conversion factor. How do you convert from energy to temperature? By multiplying by Boltzmann's constant. Okay? Okay, so these are matters of convention and nothing else, nothing more than that. So the mean square value, if I want to compute it, I go back to the generating function and I write fn of x is equal to summation h is equal to 0 to n Pn of h x to the power h, and fn prime of x is h times x to the power h minus 1.
Sir, if we double
Differentiate once again, what will you get?
we'll get why are we calculating the mean square? What does it signify?
What does the mean square signify? The value of the average value of the square of the random variable. In this case, it will, yeah, it's important. I'll tell you why in a minute. We'll see that the scatter about the mean value is measured by the mean square minus the square of the mean. It's called the variance. So we're getting to that. You see, if you have a random variable and it's got a probability distribution, something like this, then this point here, if it's completely symmetric and distribution, this point will be the mean value, right? In general, it's called the mode because that's where the maximum is. And there's a thing called the median, which is that point where the area under the curve is half on either side. Okay. But in the symmetric distribution, the mean, mode, and the mean value, they're all the same. And the median are all the same. You would also like to know, given the fact that this is the average value, it doesn't tell you how scattered this variable is, how close to the mean value its realizations are. So you would like to have a distinction between this distribution and something like this versus something like this. All the time the area under the curve is 1, but this is very close to the mean almost always. This is very far, can have very wide excursions. This is measured by this width here. The ratio of that width to the mean, that's called the relative fluctuation. That's what we're getting at. The second moment will tell you what that is. The variance will tell you what that is. Okay. So if you differentiate a second time, what happens?
H square minus h minus
Double prime. Can I put a double prime? Is that notation familiar? This becomes h
h square minus h
h minus 2. Now what happens if you put x equal to 1 after you differentiate twice?
we get h square minus h, so we can separate the summation.
So fn double prime of 1 is equal to the average value of h times h minus 1.
Which is summation of h.
Agreed? Because it's the average value of whatever is multiplying Pn of h. And you put x equal to 1 so that x goes away. But I can simplify this. This is equal to the average value of h squared minus h. What is the average value of the sum of two random variables? The sum of averages, because addition as well as averaging are both linear operations. They commute with each other. Not so when you take the mean square. The square of the sum of two objects is not the sum of squares. A plus b whole squared is not a squared plus b squared. Okay? So because averaging is simply an arithmetic operation which is a linear operation, and so is subtraction or addition, commutes, and therefore this can be written in the form h squared minus h. So if I now ask you what's the mean square in terms of the generating function, what would you say?
If double dash n of 1 plus single dash n.
Because we already found that the mean value is the first derivative. Okay. So if you got a generating function, you got all power in your hands because you can find anything, any moment at all for the random variable. Just by successive differentiation, which is very easy. And what's the scatter in this problem? What is this quantity? And this is the quantity I want to introduce now. It's called the variance variance of h is defined as the mean square minus the square of the mean. It's defined in that fashion. Okay. What's that equal to? In terms of the generating function, we already have h squared. It's f double prime of 1 plus f prime of 1. Minus f prime of 1 the whole square. So if you know how to differentiate x to the power h, you've got all the moment, you've got the variance. I now claim that this is a non-negative quantity. It cannot be negative. The least value it can take is 0. And if it takes the value 0, if the variance of a random variable takes the value 0, that variable is not a random variable at all. It's got a sure or deterministic or specific certain value. There's nothing random about it. So the variance is a kind of if and only if kind of test for whether a variable is random or not. If it's random, the variance is positive. If it's 0, it's not a random variable. It cannot be negative. Why do I assert that this quantity can't be negative?
Because you showed earlier that
I just said that by hand waving, saying that the average of a random variable could be 0, but the mean square cannot be 0 unless the variable is 0 itself. Okay. Why do I claim that? The reason is very simple and very intuitively appealing. Suppose you got a random variable, just pictorially, that as a function of time, this variable xi of t does something irregular. It's a continuous variable, say it does something irregular. We'd like to read some regularity into it. We'd like to find what's called the average value, for instance. And the average value could be dependent on time, but let's take a simple case where it's independent of time. It goes like this. That's the average value. There's fluctuations about it, but this is the average value. We would like a measure of how much the fluctuations are. Taking the average has killed it because these negative values and positive values have killed each other and given you an average value here. We'd like to measure what the scatter about this mean is. For that, you need a positive quantity. You need something like the variance to do that, because if you could square the variable, then all these negative portions below the mean would all become positive values, and then you can find out how much is the scatter about the mean. So that's what the variance does, because what it does is the following. Let's take that example itself. Suppose you consider h minus the mean value. So I'm taking the random variable and taking its average value over realizations and taking the difference of the two. Can this difference be positive or negative? Can it be positive or negative?
yes.
Certainly, there's no reason. Sometimes you get less than the mean, sometimes you get more than the mean. What's the average value of this quantity? I can do that, right? Now you see why I use this notation. What is this? Well, I already said the average value of a sum is the sum of average values. So the first term is average h minus the average value of the average value of h. But once I've already taken the average, there's nothing to average over. It's a deterministic variable, right? So this is h itself. Is identically 0. Right? But suppose I were a little cleverer and say, no, I'll take the deviation from the mean, which is h minus h, and square it.
X square minus.
Can this term become 0? You've got a sum of positive values in general because you've squared it, right? So this term cannot become 0 except if the h is not a random variable at all, as we'll see in a minute. Now let's simplify it. What's this equal to? H squared minus twice h times h plus h average squared. All I've done is to take the deviation from the mean, which is h minus the average value of h, and squared it. That's a random quantity because h is a random variable, right? Now I take its average. the average of this huge guy. What is this equal to by our rule? When you have a sum of terms and you want the average, you take the sum of averages. What's the first term?
Average of excluded x square.
Mean square minus twice average value of h times h. Average value of h is already averaged over, it's a deterministic variable. 2 is a number, so there is no averaging over 2. So it becomes twice h times h itself, plus there's nothing to average over here further because it's already an average. What's that equal to? You agree that this is twice the average value squared? It's equal to the variance of h. Now you see why I asserted that the variance cannot be negative. Because it's an average value of the square of the deviation from the mean, and because it's the average value of a square, that square cannot be negative, therefore the average cannot be negative. And when is it equal to 0? When is variance h equal to 0? Variance of any random variable, when is it equal to? When the mean square is equal to the square of the mean, that variable has no variance. But if the mean square is equal to the square of the mean, the variable is not a random variable but has only one value. Graphically it will be some delta function, some unit measure there at that point. Okay. So in the coin tossing problem, show that variance of h show that it's the number of trials multiplied by the probability of heads multiplied by the probability of tails. Now physically, when you have random variables with physical dimensions, the mean square has a different dimensionality than the mean value because one of them is the square of the variable. You want to compare quantities with the same physical dimensions, and that's done by taking the square root of the variance. So the standard deviation is the positive square root of the variance, and the relative fluctuation is the ratio of the standard deviation to the mean value. What is it for a coin toss? Yeah, I would like to have a quantity which I can compare with the mean value, which measures not the mean but the scatter about the mean. The scatter about the mean is measured by the variance, but the variance has got the dimensions of the square of the random variable. In this case, it was just the number of tosses which was dimensionless, but if I look at some physical quantity like velocity or position and so on, it will have physical dimensions. So to bring them to the same dimension, you take the square root of the variance, which will have the same dimensions as the random variables. Yeah. SD stands for the standard deviation, which is the square root of the variance. So for the coin toss experiment, what is the relative fluctuation in the number of heads? The mean number was NP, number of trials times the probability of success in a given trial. And the standard deviation is square root of NPQ. Q is 1 minus P. Therefore, the relative fluctuation is 1 over the Q and P are not so relevant, but the 1 over square root of n is very important. When you apply it to our problem of putting all the molecules of the gas in this room in one corner, that quantity Q and P depend on the ratio of the volumes and so on, but there is a 1 over square root of n. And n was of the order of 10 to the power 24, 10 times Avogadro's number. So what's the relative fluctuation in the density in this room? Proportional to 1 over square root of 10 to the power 24. 1 part in a trillion. You're safe. Thermodynamics is good to 1 part in a trillion. Really, it's the law of large numbers in action. Okay. So this is a very characteristic decay, this 1 part in 1 over square root of n is very characteristic of. Now all our considerations today have been extremely elementary, but you can see how powerful these results are getting. Okay. What's the mean number of tosses you have to make before you get a head for the first time? We had the distribution already. What's the generating function for that distribution? So we had P of n. I don't know what I use rho of n. What's the mean value of n? This is summation n equal to 0 up to capital N, P q to the n minus 1 times n itself. Define a generating function like this, x to the power n, differentiate with respect to x, so there will be an n brought out here, put x equal to 1 and do the summation, it's a trivial sum in this case. So that's an exercise for you to show that the average number of tosses you have to make before you get heads for the first time is n times p. Okay. And so on, yeah. I said that to find the average number here, to find n, what you do is to do this, differentiate, define a generating function by this method, find the derivative with respect to x, that brings an n down here, x to the n minus 1, put x equal to 1 and then you get the mean value. You can combine this qx and bring the q outside, it's just qx, again a geometric series. So you'll get something like 1 over 1 minus qx or something like that. Differentiate it. There are numerous problems where instead of algebra you use geometry, and it's called geometric probability. Let me introduce you to a couple of them and then we'll do some serious examples using that. And I start with a playful kind of example. I take a meter rule, a rod a meter long. I have an axe. I close my eyes and chop this stick into 2 pieces, into 3 pieces. So I put a cross here and a cross here. And I have 3 pieces. And let's call them label the length of each of these by x, y, and z. Okay. We had x plus y plus z is equal to 1. I completely randomly chop this stick up into 3 pieces by 2 chops at random. I close my eyes, I don't know where I'm doing it and I do it. Okay. What's the probability that I land at exactly the same point to the last decimal place in the 2 chops? You're choosing one point out of a continuum of points. And the probability of an event in a continuum, a given event, is 0 because this continuum is not measurable at all. It's not countable, sorry, it's not countable, and the probability is 0. We have to talk about probability densities, but we will ignore that for the moment and say I chop it in 2 different places and I end up with 3 pieces x, y, and z in length. What's the probability that the 3 pieces form a triangle? How would you approach this problem?
Well, we have to show that either x plus y should be greater than,
All right, x plus y.
and same for all the other ways that can be arranged.
They can't be negative. So, how do you say that?
Well, so in the first case, where the first term happens, the average of that will be in the middle, roughly. Yeah, it will be in the middle. And so, if in the first case it happens on the left side, then the second strike has to happen on the right side, and vice versa.
No, it doesn't have to happen.
For it to form a triangle,
For it to fall on a triangle, they have to. So how will you solve this problem? It's a problem in geometric probability. It involves defining measures of probability very carefully, which I'm going to ignore completely. It's not as trivial as it looks. But there's a very simple hand-waving heuristic way of doing it, which is sort of physically appealing. I need a picture. I need some pictorial representation of this whole thing. So I do the following. Can I erase this? Oh, let's leave it like that. I would like to be able to represent on the same picture all the three sides of this triangle. So I'd use xy coordinates, except that I need to represent z also in a manner which is completely symmetrical, because there's no distinction between x, y and z. What I call x and what I call y and z are completely arbitrary. Right? So let's start by saying this is the line x equal to 0, and this is the line x equal to 1. So x increases as I move perpendicular to this line. Similarly, this is the line y equal to 0, and this is the line y equal to 1. So y increases in this direction. And finally, there's a z. So let me draw this picture again. So x increases in this direction, y increases in this direction, and z increases in this direction. Sorry, z equal to 0, z equal to 1. Do you agree that all the values of x, y, z that you can imagine must be inside this triangle? Because no part can be less than 0 and no part can be bigger than 1. Okay? No part can be bigger than half, because if it's bigger than half, the sum of the other two parts is less than this part, and the triangle inequality is violated. So that's half here, and that's half here. So while this full set of possibilities of x, y, z is the full big triangle, what is the measure of the set of possibilities where you actually can form a triangle? Every side is greater than 0 but less than half.
So it's very innermost.
It has to be this triangle, the fellow inside, as compared to the full equilateral triangle, which is the full set of possibilities for x, y, z. But of that, you are allowed only that set of possibilities where the three form a triangle, which means that no side can be bigger than half, no side can be negative. And what's the area of the central portion compared to the full portion?
1 by 16. 1 by 16.
Yeah. Somebody said 1 by 4. Who's that? Yeah, 1 over 4. There are 4 symmetric triangles completely. Quite right. It's 1/4. 1/4. The central triangle has got 1/4 area of the full bigger triangle. So the answer is 1/4. Okay. We use geometry in this problem. Okay. Now I give you a second problem in geometry, right? I give you a triangle, I give you a circle of unit radius. The radius is irrelevant actually. And I draw a chord at random. So I choose 2 random points and draw a chord. What is the probability that the length of this chord, this length, is less than the radius of the circle? So let me repeat the problem, which we will discuss next time. I take a circle and draw a random chord, completely at random. And then I ask, what's the probability that the length of this chord is less than the radius of the circle? It's clear that the radius of the circle doesn't play a role here at all, in the sense that its numerical value is completely irrelevant. It will be the same for all circles. So is the problem clear? So the chord is AB, and we want probability AB is less than the radius. So I leave you to work on this problem.